Good morning, everybody. I am Vempati Srinivasulu, Assistant Professor of Chemistry, Nagarjuna Government Degree College, Nalgonda. We are discussing about coordination chemistry, which is meant for BSc second year, third semester students chemistry. In this chapter, so far, what we have discussed is what are coordination compounds, what are double salts, what are the major difference between coordination compounds and double salts, different examples for coordination compounds, then what are the terms used in this chapter. Those are coordination compounds, complex ion, counter ions, cationic complex, anionic complex, central metal atom, coordination number, ligands, chelating ligands, chelates, all all these things we have discussed in detail with examples. Then we have discussed IUPAC nomenclature. Using IUPAC nomenclature, how we name a coordination compound, different rules. So applying these rules we have discussed with so many examples. After that, we have discussed how to write formula. When we know the structure, we have to give the name. If you have the name, how we have to write the structure by following the same IUPAC rules. So we have discussed with different examples. Then followed by Werner theory of coordination compounds. What is Werner theory? What are the important postulates? So how Werner explained different cobalt complexes, primary valency, secondary valency, all these terms are explained by Werner. Then what are Werner's limitations? Then followed by Sidgwick theory of electronic interpretation of coordination compounds. In this theory, we learned about EAN, effective atomic number. What is effective atomic number? How it determines the stability of complexes, how to calculate different um, complexes, effective atomic number of central metal atom. Then what are its limitations? So all these things we discussed in the previous class. Today we are going to discuss about valency bond theory. To explain coordination compounds, we have different theories. One is valency bond theory, molecular hybridization theory, then crystal field theory. So all these theories explain formation and properties of coordination compounds. Okay, in this valency bond theory, we discuss postulates, and using this valency bond theory, we explain different complex formation and geometry and magnetic properties of different coordination compounds in tetrahedral, square planar, and octahedral complexes. So we'll go to today's class. Okay. Valency bond theory, VBT. Okay. We have valency bond theory, crystal field theory, and molecular orbital theory. Okay. Then So valency bond theory is explained by Linus Pauling. He developed valency bond theory. He received a Nobel Prize for this work. In 1954. He also received a Nobel Prize for Peace in 1962. He received a Lenin Peace Prize in 1968-69 year. So he is a eminent personality. He worked a lot to this coordination chemistry. So what are valency bond theory postulates? So we have to understand the coordination compounds. We have to know all these points. We'll discuss one by one. So according to this theory, the central metal atom or ion in the complex makes available a number of empty orbitals for the formation of coordination bonds with a suitable ligands. So what we know so far, every coordination compound should have a central metal atom which exhibits two valencies, primary valency and secondary valency as per Werner theory. Primary valency is satisfied by negative groups only, whereas secondary valency may satisfy positive or negative or neutral ligands. So for this, central metal atom has to arrange empty orbitals. Why empty orbitals? So in this compound, coordination compound, we know that metal ligand bond should occur. There should be a coordination bond between metal and ligand. So in the coordination bond, we know that electron pair, a bond forms between electron pair donor and electron pair acceptor. So how many? So it has to central metal atom of coordination compound has to provide required number of vacant orbitals. This is the first point. So coordination compounds, central metal atom has to provide required number of vacant orbitals. If it is going to bond with 6 ligands, it has to provide 6 empty orbitals. If it doesn't provide 6 empty orbitals, it doesn't form any complex. So this is the first point. Coming to the second point, the appropriate atomic orbitals s, p, d of the metal hybridize to give a set of new orbitals of equivalent energy called hybrid orbitals. You see, what is second point is hybrid orbitals. Is important. So the required number of first point is it has to provide required number of empty orbitals. These empty orbitals having different energies. So with these different energies, it doesn't form equivalent bonds. That's why it is explained through hybridization. So all available orbitals which are going to take part in coordination bond intermixes together. What which process we call is hybridization. So S, P and D orbitals undergo hybridization. We know what is hybridization. After hybridization, we get equal energy orbitals of equal. So equal number of orbitals. Some number of orbitals undergo intermixing. After that, it will give equal number of orbitals with equal high energy, but the two equal energy. So that is the importance of hybridization. So second point is the orbitals s, p, d orbitals of metals undergo hybridization. Due to this hybridization, we get orbitals of equal energy. All our orbitals are equal in all manners. This is the second point. Coming to the third point. What is the third point? The d orbitals. You see, the d orbitals involved in the hybridization may either inner n-1 d orbitals or outer n d orbitals. This is the third point. So we have d orbitals, 3d orbital, in the 3D series, we have 3D orbital and 4D orbital. In 4D series, we have 4D orbital and 5D orbital. In 6D series, we have 6D orbital and 7D orbital. Okay, vacant. So in the case of 3D orbitals, we see there will be possibility in participation of hybridization is two possibilities: n minus 1D orbital, nd orbital. Nd means 3D, no, nd means 4D, n minus 1D means 3D for 3D series. So there is a two chances are there. Two types of orbitals may participate in terms of d orbitals. If 3D orbitals participates, it's called n minus 1D. So these complexes are called inner orbital complexes. Whereas in which if d orbitals participates, outer d orbitals participate in this hybridization, we call as outer orbital complexes. So as per the orbitals involved in the hybridization, we classify these two types: inner orbital complexes, outer orbital complexes. Inner orbital complexes are the complexes in which n minus 1 d orbitals undergo hybridization. In the case of 3D series, 3D orbitals participates. In the case of 4D orbitals, 4D series, we understood that 4D orbitals undergo hybridization. Whereas outer orbital complex means in 3D series, 4D orbitals take part in hybridization. So that's why depending upon d orbitals of which type is undergoing hybridization, we have two type of complexes: inner orbital complexes or n minus 1d and outer d orbital complexes. Okay, then coming to the next point, each ligand has at least one orbital with two electrons or lone pair of electrons. So what we discussed in the earlier class, what is a ligand? Ligand is a group which contains a lone pair of electron and an atom, and it should be able to donate this electron pair to the central atom in the formation of coordination bond. So that is mentioned in this point. So as per this point, so a orbital should have an electron pair and it is capable of donating this lone pair of electrons. This is the this is the one point. Each ligand has at least one orbital of donor atom containing a lone pair of electrons. Then next point. You see, next point. The empty orbitals of metal ion overlap with the filled orbitals of ligand to form a covalent sigma bond, that is ligand to metal bond, L to M. The bond is also called a coordinate bond. So in this point, as per this point, a bond is forming between central metal atom and ligand. Which manner? So ligand is donating electron pair which has a lone pair of electrons on a atom, donor atom, which is available freely. That means lone pair. So central atom has to accept this donating pair from ligand. It has to provide a required number of orbitals. So as per this theory, the ligand metal bond is coordinate bond. That means a bond means interaction of orbitals, overlapping orbitals should occur, we know. We have know as per our previous knowledge, a bond is a bond which where a overlapping of orbitals two different orbitals of different atoms should occur. So as per this theory also, a new coordination bond is forming between overlapping of empty orbital of like metal, empty orbital of metal, and a pair of a orbital, an orbital which has a lone pair of electrons of a ligand. So these interaction, this overlapping of these orbitals, filled orbital of ligand, vacant orbital of metal is taking place. So due to this interaction of filled orbital of ligand and vacant orbital of metal, a bond formation taking place from ligand to metal, which is also known as coordination bond. So this is a valency bond theory. As per this theory, we can explain formation and properties of different complexes in this syllabus. So these are the important postulates of valency bond theory. As per this theory, so once again, metal atom has to provide required number of orbitals, vacant orbitals. After that, these orbitals undergo hybridization. Depending upon which type of d orbitals participating in hybridization, we have two types of complexes: inner orbital complex, outer orbital complex. Ligand has to provide a lone pair which is free available on donor atom of ligand. Finally, interaction of this filled orbital of ligand and vacant orbital of metal is taking place. Due to this interaction, a coordination bond is forming from ligand to metal. In this way, we can say the formation of bond is nothing but acid base, salt formation from acid base. We know as per Lewis theory, electron pair donor is a base. In this, ligand is acting as base, whereas metal electron pair acceptor is a metal. In this case, it is a acid as per Lewis theory. So from base to acid, electron transformation is taking place. So this is formation of coordination bond in coordination compounds. So this is a okay. We'll discuss first tetrahedral. Okay, you see. Okay, you see. You take this one. Example is, what is the compound? It's a complex ion. The name of the compound is uh, tetrachloronickelate 2 ion. I repeat, tetrachlorido or chloro. Okay, no problem. Tetrachlorido nickelate 2 ion. It's a anionic complex. So in this complex, we apply our valency bond theory to this complex. Okay, what is this? It's a complex ion. It's an anionic complex. In this complex, central metal atom is nickel. So atomic number of nickel is 28. We know the outer electronic configuration is for argon 4s2 3d8. So this is the electronic configuration of okay, nickel 28. So as per from this, we can say that see once again. Okay, this is a electron distribution. So 4s2 3d 4s2 3d8 actually. So in nickel, this complex, nickel is exhibiting +2 charge. So 4s2 3d8 in +2 state 4s0 4s0. That means it has d3d electrons, 8 electrons, in which 2 electrons are unpaired and 3 pairs. In 4s and 4p are vacant. Okay, so it has to bond with 4 chloride ligands. From the complex, we have to understood that it has to provide 4 vacant orbitals by nickel. So 4 s orbital, 1 s orbital and 3 p orbitals mixing due to this mixing we get 4 sp3 orbitals. Due to hybridization, sp3 hybridization will get 4 sp3 orbitals of equal energy, which arranges in tetrahedral geometry. Okay, this 4 sp3 orbitals are vacant orbitals, which is ready to accept electrons from ligands. So due to interaction of this 4 vacant orbitals, 4 sp3 orbitals, they accept electrons from chloride ligands. So due to this interaction of 4 chlorine atoms like vacant orbitals of full which are having electron pairs interact with this sp3 orbitals of nickel ion. Due to this, a bond formation takes place. 4 bonds takes place, sp3 and p. Okay, so that's why the nickel in this complex, nickel hybridization is sp3. It is between sp3 hybridization. Then geometry is tetrahedral. From this we can also uh, expect that this compound is paramagnetic. Why paramagnetic? It has unpaired electrons in d orbital, unpaired electrons of d orbital. So that's why it is in. This is also proved by experimentally. So this is a explanation of valency bond theory to this complex. Tetrachloronickelate 2. In this complex, nickel exhibits sp3 hybridization. It provides 1 s orbital and 3 4p orbitals. After intermixing of these orbitals, which is called sp3 hybridization. Due to this sp3 hybridization, the complex, these orbitals arranges tetrahedral geometry. These vacant orbitals overlaps with the filled orbitals of 4 chloride ligands. That's why 4 bonds forms between these chlorides and nickel. Hence, it is in tetrahedral geometry. Experimentally, it is proved that it is a paramagnetic in nature. So this paramagnetic property is explained by two unpaired orbitals in d orbital, 3d orbital. So this is the valency bond theory explanation of tetrachloronickel complex. Okay. As per this theory, if we can expect as per number of coordination number, we will expect the geometry and hybridization. If you see 2 coordination number. It undergo sp hybridization. It is in linear shape. For example, this is a complex for linear shape complex with sp hybridization. What is this complex? Diamine silver 1 Ag argentinum 1 ion. It is sp hybridization. It is in sp hybridization. The central metal atom exhibits sp hybridization. So coming to sp number 3, the coordination number with 3, we can expect a sp2 hybridization 3. So it is in trigonal planar shape. So these are the two examples for trigonal shaped coordination complexes. Triiodomercurate 2 ion. Then second one is tris trialkyl phosphine argentinum 1 ion. So these two examples for coordination number 3 with trigonal planar geometry. Coming to next 4. So you see coordination number with 4, it may present in two, it may appear in two types of geometries. You see 4 may sp3 or dsp2 hybridization. If it exhibits central metal atom exhibits coordinate number 4 sp3, we expect a tetrahedral geometry. For example, tetracarbonyl nickel 0, tetraamine zinc 2 ion. These are examples for tetrahedral geometry. Coming to 4 coordinate number with a dsp2 hybridization. So we exhibit a square planar shape geometry. So examples for these square planar complexes are tetraamine platinum 2, tetracyanide nickelate 2 ion. So these two examples for square planar complexes. Coming to coordinate number 5. Coordinate number 5 sp3d. Coordinate number 5 also exhibit sp3d or dsp3. If it is sp3d, we expect a square pyramidal shape. Or dsp3, we can expect this trigonal bipyramidal. Square pyramidal, trigonal bipyramidal. For example, square pyramidal pentafluorido stibnate 3 ion. For trigonal bipyramidal, the example is pentacarbonyl iron. So these two examples for complexes with 5 coordination number. Coming to the 6 coordination number, you know that 6 coordination number have two types of hybridization: D2sp3 for inner orbital complexes and sp3d2 for outer orbital complexes. These two types of hybridations also exhibit octahedral geometry. Octahedral geometry. Okay, so this is a octahedral geometry. You see this one. So examples for this is hexacyano ferrate 2 or hexafluorido cobaltate 3. So these are the different examples for coordination compounds with different coordination numbers. So we can expect a geometry if you know the coordination number of a ligand or central metal atom or complex. Then we'll explain this with different examples. So one more example for tetrahedral complex. You see, okay, tetra. For example, the we are applying valency bond theory to coordination compounds. For example, if you take this tetraamino nickel 2, tetraamine amino no amino amine, since it's a neutral ligand, tetraamine nickel 2 complex, nickel 2 ion. So in this also nickel is a central metal atom. So atomic number of nickel is 28. You know the electronic configuration zero atomic state. Zero oxygen state is a 4s2 3d8. You see, in this state, 3d at has 8 electrons, 3 pairs, and 2 unpaired electrons. 4s at has 1 electron pair, 4 p are vacant. So in this case, we have only 3 orbitals. Okay, we require 4 orbitals. That's why in this nickel plus 2, in this complex, nickel is exhibiting plus 2 oxygen state. So in the plus 2 state, this is a electronic configuration of nickel ion in plus 2 state. So 4s0, 4p0, and 3d8. So in this state, nickel plus 2 oxygen state, we have 4 vacant orbitals. These vacant orbitals undergo sp3 hybridization. Before, we have different energy. 4s is different, having less energy than 4pi. We know that. So after mixing up this 4s 1 orbital, 4p 3 orbitals, we'll get 4 sp3 orbitals. These 4 sp3 orbitals are undergo overlapping with 4 amine ligands. Due to this interaction, we expect 4 coordination bonds. So these are that electron pairs. What we are showing is these electrons are accepted by ligands. You see. So these are the original electrons which has a central metal atom of nickel. So these are the electron pairs received from ligands. In this way, we expect bond formation in tetraamino nickel 2 ion complex ion. So in this, so nickel is exhibiting sp3 hybridization. Due to this sp3 hybridization, it appears in tetrahedral geometry. So like this. So this way. So this is a okay. This is a central is nickel. One is ammonia molecule. One ammonia. One ammonia. One ammonia. So this is a tetrahedral shape. Okay, tetrahedral shape. So it is also exhibiting paramagnetic property. This paramagnetic property is explained by it these two electrons in d orbitals. We know d orbitals containing vacant unpaired electrons of d orbitals is one of the reasons of main reasons of exhibiting of paramagnetic properties. So this compound exhibits paramagnetic behavior. This behavior is due to presence of these two unpaired electrons in 3d orbital. So this is a explanation of valency bond theory. So we are applied valency bond theory in this complex, that is a tetraamine nickel 2. Next slide. So we'll explain once again one more complex. It is you see, this is a tetrachlorido nickelate 2 ion. Why nickelate? It is a anionic complex. In this, nickel is central metal atom. It is bonding with 4 chloride ligands. So we know central atom is a nickel. Once again, it is having atomic number of 28. In the ground state, it is electronic is argon 4s2 3d8 4s2 3d8 4p is also vacant. So this is electronic configuration 0 state. In the plus 2 state, if it loses 2 electrons from 4s, that's why 3d8 4s0 4p0 is the electronic configuration of nickel in plus 2. So this 1 4s orbital and 3 4p orbitals undergo intermixing. Due to this intermixing, we expect 4 sp3 orbitals. 4 sp3 orbitals. These 4 sp3 orbitals arranges tetrahedral around the central metal atom of nickel. So these 4 sp3 orbitals overlap with the chlorine atom filled orbital it forms four bonds with nickel, four coordination bonds with nickel. That's why it is appears in tetrahedral geometry. So like this geometry. This is a explanation of uh, tetrachloronickel. Since it experimentally it is proved that it is a paramagnetic property. This paramagnetism is attributed from this unpaired electrons of nickel in 3D atoms. This is the valency bond theory explanation of tetrachloronickelate 2 ion. So once again, tetrachloronickelate ion, nickel is a central metal atom. It is exhibiting sp3 hybridization. Due to this hybridization, the four sp3 atoms arranges tetrahedrally around the central metal atom. These four sp3 atoms overlap with the four chlorine atoms filled orbitals. Due to this overlapping of filled orbital of chloride ligands and vacant sp3 orbitals of nickel ion, there is a four coordination bond taking place between chloride and nickel. Four metal ligand to metal bonds. Further, the paramagnetic theory of this compound is explained by the presence of two unpaired electrons from of nickel. So these two electrons. This is the valence bond theory explanation of tetrachloronickel 2. One more example. So already nickel tetracarbonyl nickel. So this is a tetracarbonyl nickel. IUPAC nomenclature is tetracarbonyl nickel. Carbonyl is a neutral ligand. That's why we are telling as such carbonyl, carbon monoxide. Okay, in this also central metal atom is nickel plus 2. So generally nickel plus 2 complexes exhibit this coordination compounds with this type of ligands. The same nickel plus 2 in the different ligands, it may exhibit different geometry, different hybridization. That's a different thing. We'll discuss later. So in this complex, nickel is zero oxidation state. That's why uh, it is a 4s2 3d8 in ground state. In zero excited state also zero state, but this 4s electrons come to the 3d orbital. You see pairing up taking place. Presence of carbonyl ligand, electron redistribution taking place. So 4s electron coming to 3d orbitals. So now 4s orbital is vacant, and with the 3d10 electronic configuration, 4p orbitals also vacant. The intermixing of this 4s and 4p orbitals will expect sp3 hybridization. Due to sp3 hybridization, tetrahedral 4 sp3 orbitals with tetrahedral geometry. So nickel atom exhibits tetrahedral geometry. So these four tetrahedral sp3 orbitals overlaps with the four carbonyl ligands. Carbonyl. So these carbonyl ligands groups act as ligands, neutral ligands. This electron pairs, vacant electron, unpaired electron pair of carbonyl group overlapping taking place with vacant orbitals of sp3 orbitals of nickel. So due to this overlapping, we expect four sp3 p bonds. So this is a explanation of tetracarbonyl nickel. So in this complex, nickel is exhibiting what? Nickel is exhibiting sp3 hybridization. So this compound is diamagnetic in nature. This diamagnetism is explained by with the theory successfully. So okay, because of having doesn't having an unpaired electron, so that's why in d orbital, that's why it doesn't exhibit any paramagnetic property. That's why it is a diamag. All electrons are paired in 3d orbital. So you see in 3d orbital is having 5 electron pairs. That's why it is diamagnetic. So once again, nickel tetracarbonyl nickel is a neutral complex. In this central metal atom is nickel. It is exhibiting sp3 hybridization, 4 coordination bonds with 4 carbonyl ligands. it is diamagnetic in nature. So this is a explanation of valency bond theory of different complexes. So far, what we have discussed in this class is what are the different postulates of valency bond theory. Once again, I repeat, as per valency bond theory, every metal atom has to provide required number of vacant orbitals. These orbitals undergo hybridization. Two types of hybridization. That means two types of complexes: inner orbital complexes, outer orbital complexes. Then a ligand has to provide an electron pair which is available in a lone an orbital of donor atom. Then an overlapping of filled orbital of ligand with vacant orbital of metal is taking place is nothing but there is a coordination bond is forming taking place. In this way, we applying these points. This theory is applied to different complexes with the four coordination number with tetrahedral geometry with sp3 hybridization. So in the next class, we'll discuss this. We apply this theory to square planar complexes and octahedral complexes. Okay, we'll see in the next class. Thank you very much.